Hello all, so in this video we will discuss minimum in rotated sorted array problem. So we have already seen how to find or search an element in a rotated sorted array. So here just the trick is to find the minimum. Okay, so we have seen both the versions of rotated sorted array to find an element when there are unique elements and when there are duplicate elements. So we'll also do the same. We'll also solve the problem which is its second version or its extended version, which is this one. So we will see both of them, but let's start with this one now. So firstly, it's given that again the sorted array has the unique elements, okay, and we have to return minimum. Now one thing that we can simply do is just use the minimum function, right, and we'll get the minimum, but it will take O of n, right? But our question says to write an algorithm with O of log n, and that's the reason we need to be using an algorithm which is binary search. Nothing new in that. We did so both these problems are similar, like searching in a rotated sorted array and finding minimum. So please do watch that other lecture as well. You will find it in the playlist. So now firstly again I'll just repeat what is rotated sorted array. So for example, let's say I'm given an array. Let me write 0 1 2 and 4 5 6 7. Now this is a sorted array but not necessarily rotated. Okay, now if I'll rotate this once, then everything will be shifted, right? So what we'll get is 7 0 1 2 4 5 6, correct? Now if I'll repeat this process 4 times, then I'll get this one. Okay, so that's why it's called rotated sorted array. But we are also given the amount of times you can rotate, so we can rotate n times. For example, n is the length of the sorted array, and we can just rotate n times. So if we'll rotate this 7 times, then we'll again get back the same. Okay, so that's why we can say that this is also rotated sorted array, but it's just rotated 7 times. Okay, so let's focus on building an algorithm. And so we have already seen one important property of rotated sorted array is that at least one half is sorted. Okay, and we will use this property because we know that at least one half is sorted. It's an important property for a rotated sorted array. So what does this mean? One half is sorted. So for example, this is the rotated sorted array, and we'll firstly find mid. So firstly, let's say this is low, this is high. So this will be mid. It's an odd length, so this will be perfectly, we are getting the mid in between. Now, if you see this much, then it's unsorted. But if you see from 2, we have to consider 2, okay? From 2 to the end, it's sorted. We can always say that at least one half is sorted. And if both half is sorted, for example, this and this, then it's already a sorted array, okay? So, because as I said, if we rotate this 7 times, we'll again get the same array. And that's why this property is correct, that at least one half is sorted. Okay, in this case, both sides are sorted. But so we can say that either it's not rotated at all, or we can say that it's rotated it's n number of times. Here n is 7. Okay, so that's the recap of last class. Now let's try to focus on finding the minimum. Okay, so let me remove a lot of stuff which is not needed. Now let's focus on this part. That always we can see that the minimum will lie on which side. So what I mean is that the minimum will always lie on the unsorted side. So for example, if you see this first half and this is the second half, and you can see that this first half is sorted. In the second half, this is unsorted. And minimum will always lie there at the unsorted side. Why? Because if it's sorted, then we know that it will increase, right? Then if it never decreases, then the very first element is our minimum. That's so simple, right? So it's always, if I plot graph for this, then it's like 4 5 6 7, it's increasing, and then we are going suddenly to 0, and then we are increasing again, 0 1 and 2. Okay, this is 0 and we are going to 1 and 2. This is 4 5 6 7. So this is the unsorted side. So it always lies on the unsorted side. So what we will do that is make use of binary search. So let's begin step by step using binary search. For example, let's say this is our low, this is our high, and this will be our mid. So firstly, I'll check if my left half is sorted. If it's sorted, we will discard this array and we will simply move our low to mid plus 1. So now only this much is my array that is left, and we'll again find the mid. Okay, but the important thing is, if we have the sorted array, then very first element is the minimum, right? So we can make use of this property that if the array is sorted, and how we will check that? So first things first, we will check that if my existing array or the current array that we are getting, okay, we have discarded this much, right? Because we know that our minimum will lie on this side for this array. So how can we check that my array is sorted? Just forget about the entire array. Just consider that we are given an array of 0, 1 and 2. How we can check whether it is sorted or not? Simply we can compare my nums of low with nums of high. And if it's less than or even equals to, now why equals to? Because for example, we have just array of size 1, then low and high, or not even size 1, let's consider 2, 1. It is also rotated sorted, right? So firstly, we will start with low here and high here, and our mid will be here. Correct? Let me change the color. And now we will see that left half is sorted because one element is already sorted. Correct? Because mid is lying over there. So left half is sorted. So we will move to our low to mid plus 1. So now low is here, high was already here, and the mid is also here, right? Now you can see that low and high both are at the same place, and that's why this equal to is needed. And we know that this is the minimum. So we'll simply return whatever is the minimum element, which is nums of low. We can simply return that, correct? So that's the reason that we are using equal to sign. So let's try to code this out using the binary search only. So first things first, we will go with low as 0 and high as, of course, n minus 1. And let me define n as well, which is length of nums. Now we will start our binary search that while my low is less than or equals to high, that is my low and high don't cross each other, we will continue. So firstly, we can check if our array is already sorted. Okay, that is less than, my low is less than or equals to nums of high. Okay, then we will simply return the first element, because we know that if it's already sorted, then first element will be our low, and I explained already why this equal to is needed. But if it's not, then we will continue with finding our mid. And as I already said, why we are doing this, to avoid the overflow, integer overflow. Okay, just mathematically it's the same, low plus high by 2, you can do that. Now firstly, we will check. Now what if my mid is, so one thing I forgot to explain is that how we will check whether it's a minimum or not. So let me explain it again, that how we will check whether my any element is minimum or not. So the condition to check the minimum here is if it's smaller than both of its neighbors. For example, 0 is minimum here, and you can see that it's smaller than both of its neighbors. For any other element, 5, you can see it's not smaller than both of its neighbors, so it's not the minimum. Only 0 is the one that satisfies. For example, let's say firstly we find the mid, and at mid, if we find the minimum, then we are good, right? So how we will find the minimum? That we have to check whether my mid is less than both of its neighbors. So if it's less than nums of mid minus 1, and my mid should be less than nums of mid plus 1. Now you might ask, what about the boundaries when there is no left neighbor? And what about the boundary on the right side when there is no right neighbor? Right? In order to do that, we will just put this condition. So let me just write it nicely, neat and clean, and then I'll explain what I did. And same thing we'll write here, that if my mid equals to the last element, or, and let me have the correct braces. So what does this mean is, when we are at the left edge, then we don't have mid minus 1, right? Then we won't check this condition, because we know that in OR, if any one is true, we are not checking the next one. So if this one is true, we are ignoring the next one. Similarly, when we are at the edge on the right side, then we know that there is no mid plus 1, right? So we are just ignoring it, because if this is true, then the condition will be satisfied and we will go in. But in between, it's the end, because we need it as a minimum, okay, press both of its neighbors. So if this is the condition, then we are perfectly at our mid, and sorry, we are perfectly at our minimum, because minimum is at mid, and we can simply return nums of mid. But what if this is not the case? Then we will check whether my left half is sorted or not. Okay, because we know that at least one side is sorted. So check for left sorted or not. So how we can check my left half is sorted or not? By checking if my nums of low is less than or equals to nums of mid. We can check like this. Again, equal to is needed, because when low and mid are at the same position. Okay, if this is the case, then we can say that left half is sorted, and we will move to the right side, okay, on the right half. And if it's not the condition, then we will move towards the left side, correct? So it's like we are moving the other way around. So for example, let me show you that. So for example, if this is the condition, that's 7 0 1 2 and 4 5 6. Okay, this is also a rotated sorted array. So firstly, we will start with low and high. This will be our mid. Firstly, we will check is low is less than high. No. So first condition is not satisfied. So then we will find our mid. Now we will check if my left half is sorted. Now also we will check if my mid is smaller than its neighbors. No, it's not. So both first two conditions are not satisfied. And now we will hit this condition. Okay, these two are not satisfied. Okay, so we are hitting this condition now. And we'll check if left half is sorted. No, left half is not sorted. So we will hit the else condition. And where we will be hitting? We will be hitting here. That high will be mid minus 1. Correct? Now we are discarding this much, and we are just left with this much. Now again, this will be mid. Now we will check if it's sorted or not. So we can simply say that this is low, this is high, and this is my mid. So we will simply, obviously, firstly, again, we will check first if low is less than or equals to high. No, it's not. Okay. And then we will check another condition by finding the mid, that is my mid less than its neighbors. Yes, here it's less than its neighbors. Then simply we will return mid, and we know that 0 is at mid, right? So that's how this condition of going on the either right side or the left side works. Okay, and let me try to submit it. So yeah, it's working, and obviously our time complexity will be log n, because we are every time reducing the search space by half, and obviously we are not using any extra space, so it should be constant. Now, as I said, let me show you a similar question. Okay, just here the duplicates are allowed. So in the second version, what we are given is just that our nums contains duplicates. Okay, so it's just the follow-up of the previous problem, finding minimum. So everything remains the same. You can see that everything else remains the same, but I'll try to compare the minute details. And this is tricky to come up with, and that's why it's a hard problem. But next we will discuss the smallest method, okay, which is this one. Okay, and it's super easy. So we will see that, and then you don't have to. But since to build the logic, because binary search is one of the basic building block of starting the data structures. So just to build the logic, I'm covering it. So don't worry if you don't get it, but you will get it. Just do some whiteboarding, as I said. It will be fine. So everything else remains the same. So let me show you that. So you can see this is not needed as of now. So this is the code that we have already ran and it's working fine. And now I want to show you this, that here it was less than or equals to, and I explained why equal to is needed, right? But here equal to is not there. Why? Because that's the first change. Okay, why? Because in this case 313, let's see on the blackboard so that it's clearer. For example, for 313, what will happen? This will be low, this will be high, and of course this will be mid. Now firstly we will check is my low is less than high. So firstly this will be checked. Okay, and in this case low and high are equal, right? So if I write equal to, then I'll get answer as 3, because this will be satisfied and we will directly return. And that was the reason that this equal to was removed. That's the first change. Now the second change is this condition, that when my low and high are equal. So for example here low and high are equal, right, in the very first iteration. Then of course we have to move ahead from that. Okay, so what I mean with move ahead is that when my low and high are equal, correct, then either we have to shift low to the next position or either we have to shift high to the next position. So you can do both. Okay, but I mean you can do either of them but not both. Okay, because any of one of them can be minimum. So what I mean is, if this is the case, low and high, then what you can do is either shift low by this or just shift high by one step. Of course high will be shifted to left side. So just do either of them, not both of them. Okay, and I will show you what you have to change when you change low to +1, or you can also do with high -1. So I'll show you both the cases, but let's first talk what are the differences. So here this is not necessary that we need to do both the things. And why? As I said, for this cases when my high and low both are equal, then we have to either move one of them so that we can move to finding the minimum. Okay, so if this is the case, we will just move either of them and just continue. Okay, that's the next condition. So only that is the condition, that is the extra one here. Okay, and one more thing here, if you notice, because all the elements were unique, right, in this case. So in this problem, this is the first problem. So here equal to sign was not needed, but here equal to will be needed. But equal to is not needed in both the cases, it's just needed in the second case. So this logic is tricky, right, to come up with. And why the second case? Because of these two conditions, these two test cases. If you consider for 3331, then let me show you that what happens when we consider for 3331. It will give us wrong answer. So let's do that. Mistake. Yeah, you can see 3331 we are getting 3. Why we are getting 3? Because we'll start first with low and high as here, and first condition will not satisfy. So we'll find the mid, and mid will be this case, this one, right, 3 at index 1. Now we will check if this is equal. No, low and high are not equal. We will check for this, and this condition will be satisfied if I put equal to here. Why it will be satisfied? Because we are not at mid is here, right? So it's not at mid equals to 0. So this will be checked. And if we put equals to, then the previous element, that is mid -1, which is this one, is equal, right? So this condition is true. And now let's check for this condition. For this condition, equal to is needed. Okay, so for this condition, it will be also satisfied. Why? Because we have repeated elements and mid plus 1 are equal. So it will directly return 3, and that's what we are getting. Okay. And that's the reason that we don't need equal to here. And if we run, it will work. But what if I'll remove this equal to? If I remove this one, then also it will fail. And it will fail for this case now, that 3, 1, 1. And again, we are getting 3. Why? Because if we start from low and high, then this will be mid. Correct? We will check first condition, is low less than high? No, it's not. So we will move here. Is low is equals to high? No, it's not. So we will move here. And here you will see that my mid is here, right? So first condition will be checked here. Is it less? Yes, it is less than 3. 1 is less than 3. And the second condition is it less than mid plus 1? Correct? So mid is this one and mid plus 1 is this one. So what will happen is this won't be satisfied. So we will move our low. So we will check now this condition, that whether my low is less than or equals to mid. No, it's not. So we are hitting this case, that my high will be mid minus 1. So low and high and mid, everything will be at the same place, which is at the first index now. Now again, next iteration, is low less than high? No, they are equal because everything is at the first place, low, high and everything. So mid will be also at the same place. Okay, so now we will go with this case, that is my low equals high. Yes, because it at the same place. So we'll just shift low by 1. Okay, so now this condition is not satisfied because low and high crossed each other, and we are directly hitting nums of high, and high was just here, and that's why we are returning 3. So what I mean to say when we can say that we can also do this, but for this case here you have to return low. So if you shift high, then we have to return low, and if you shift low, then we have to return high. That's the only thing, and I hope it's intuitive. So here we need equals to, or else this won't be satisfied. Yeah, so it's working, but all these things are so tricky, right? Like it worked for this case, like for searching in a rotated sorted array, it was perfectly fine. But for minimum, because of this condition and with the duplicates, it's getting really messy to consider all the edge cases. And that's why the simple algorithm will be that we won't do all these things, right? We will just compare in a rotated sorted array. We just compare with nums of high, that is right side. So what we will do is we will compare mid. Firstly, we'll find mid and just compare with the right side. So that's the logic I have already written. So let me just uncomment that so that it's clearer. And also we are using low less than high. So when low and high are equal, this loop will stop, unlike this loop. Okay, so this is important in binary search to know the difference, that when this will be useful. So always compare with the right side. So firstly we'll find mid, and we will always compare with the right side. If this will be the case, then obviously we know that if my mid is greater than nums of high, then we will simply say that my right half is unsorted. Okay, so we will move to right side. Our low will be mid plus 1. Else if when it's other way around, then we will obviously minimum is on the left side, but including mid, and that's why we are going until mid. We are not doing mid minus high equals to mid minus 1. Okay, we are not doing like this, but rather we are going until mid, and that's why this condition we are using. And when they are equal, and else, then this is the case when these two are equal. So low is not in the picture at all. And why it's low is not in the picture, let's see that. So I asked a good prompt to the ChatGPT. So we compare, because the rotation point or the minimum is guaranteed to lie in the unsorted part. That's I already said that unsorted side will have the minimum. So the right hand comparison helps us reliably detect which part is sorted versus unsorted, even though there are duplicates. So for example, the rightmost element gives us a consistent reference whether the right half is sorted or not. So once we detect the sorted half, the minimum must be in the other half, that is on the unsorted side. For example, consider the same example that we are taking. So for case 1, what will happen? Low and high and mid. So we will check mid and high. Since mid is greater than high, it means the right side is unsorted, so our minimum lies on the unsorted side. And if it's other way around, case 2, then obviously right half is sorted, so the minimum is either at mid or it's on the left half, or it means left to the mid. Okay, and now you might answer question, why not compare with the low? So consider this example. If you compare low with mid, this will be mid, I guess. Yes, so they are equal, right? And this doesn't give any information whether which part is sorted. It's ambiguous, right? And that's the reason that because it's equal, it doesn't give any information. But if you compare here with high, then directly you will get that which side is the minimum. That minimum is on the right side. Okay, so that's why high is more reliable, and that's the reason to write this. And it's so simple, right? Rather than this complex thing. So for this problem that we already discussed, right, even it's its first version, both are equal only. So for this, it's fine if you use this method, but for this case, it's a bit tricky, okay, to come up with all the edge cases. And obviously in the interview regime, it's so hard to come up with all these edge cases, and that's the reason I'll recommend to prefer this and just try to write on it that why we are using. And obviously we can return either low or high because both are equal, so it doesn't matter if you return low or high. And the same thing I can do for this as well, and I already did that. So let me show you in my submissions. In one of my submissions, maybe, yeah, so you can see here that I have just do by comparing on the right side, same as problem 154, which is this one. Okay, it's the second version of it. Just compare, and obviously we will go until mid. Okay, not mid -1 because we are using low less than high. So that's the edge case. So it's simple. Here we don't need the equal to check, correct? So here it will be just two conditions, if and else, and that's it. Okay, so what I mean by equal to check is this one. This we won't need, so we'll just have two conditions, if and else, and that's it. So that was about this problem. It's a bit trickier, I know, but if you write on with the whiteboard, it's gonna be fine. So thank you and stay tuned.